Hello, this is a lecture on section 1.4 of linear algebra with David Lay. This is Karen Edwards talking to you and making annotations on the transparencies. So this section 1.4 is about the matrix equation. It's just a different way to write what we were already doing in 1.3 and in the previous sections. We're just writing all that stuff with a slightly new structure and notation. What we were doing in 1.3 is actually down over in this part. We were talking about linear combinations of vectors. So that's what this is. This is a linear combination of vectors. And remember, we discussed in 1.3 that a bold letter represents a vector, so that's actually a whole column of numbers there. Each of these A1, A2 through AN represent columns of numbers. And then X1, X2 through Xn are the weights for those column vectors. So we're taking some combination of A1 through AN with X1 copies of A1 and X2 copies of A2 and Xn copies of AN. So that's what we did before. Now we're going to write it a new way over here, which is the matrix equation. And this is actually a special case of matrix vector multiplication. So that's mentioned up here. And matrix multiplication is covered in 2.1 for C2.1 for general matrix multiplication. Sorry, I can't write as well on my tablet as I can on the tablet in the classroom. Writing's a little more scrawly. So without going into the full idea of matrix multiplication, what this notation means right here is that, again, you have a matrix, which you're going to think of as a bunch of column vectors. We'll see an example in a moment. And then that set of column vectors is multiplied by this column with the x1, x2 through xn. And what that notation means is take each vector a1 through an and multiply it by its corresponding weight, x1 through xn. In other words, it means what we have over here again on the right. But that's just a different way of writing it. So let's look at an example, make it more clear. So if we are given a matrix, and again, think about the columns of that matrix, and that matrix is multiplied by a set of weights, then the weights correspond to the columns. So the first column 130 here gets multiplied by the 7, and the second column, negative 425, gets multiplied by the negative 6. And that's exactly what happens next. So it's sort of like you take the 7, negative 6 and sort of rotate it sideways in a sense, and then put it in front of each column as the corresponding weights. This will all make a lot more sense once we get to matrix multiplication and you see what's going on in general. But in this case, the 7 and the negative 6 are the weights or the coefficients of the columns. Then you can just multiply the weight by the column. You get 7, 21, 0. Multiply negative 6 by that column, you get the 24, negative 12, negative 30. Then you add those two vectors to get the 31, 9, negative 30. Okay, so, oops, let's see, next page. I guess I have to, like this, okay. So now we're going to, sorry, I'm still getting used to my tablet here. Now we're going to practice this notation in an actual example. So they're giving us an augmented matrix, and I like to put my little augmenting there, the line to show the augmenting. This is what we really started out with at the beginning of the semester, and we know that this corresponds to the following system of equations. Now notice when you have I'm about to write down system of equations, I need variables, and there's no variables given in the matrix. So you either have to make up variables or because they have a little x here, that usually is written as x1, x2 through xn, so those are our variables. Often, if you want to keep track of them with the matrix, I write the little variables up at the top. It's a good place for them if you want to keep track of them. So it corresponds to the system 2x1 plus 3x2 plus 4x3 equals 9. And the second row gives us negative 3x1 plus 1x2. And you can skip writing this, it's plus 0x3. I'll put it here because it'll help for the other ways of writing it below. Okay, so those are what we started the semester with. Then we realized we could rewrite this system of equations as the vectors. So the vectors are these columns, and 2, negative 3 has the x1 weights, 3, 1 is multiplied by x2, 4, 0 is multiplied by x3. So you should be able to see the correspondence between those two ways of writing it. In the system of equations, each equation corresponds to one row of the vector equation. Okay, and now the new matrix equation is just a way of writing these weights of the column vectors. So we write all the column vectors first, 2, negative 3, 3, 1, 4, 0, and then multiply it by the column vector of the weights, x1, x2, x3, and it should equal 9, negative 2. Now, if you look at this, you might think that the x1, x2, x3 looks like it's sticking out below, and is that correct? So it is correct because, again, x1, x2, x3 gets sort of rotated sideways, horizontally, to become the weights. So what matters is that the number of, just a different color for fun, what matters is that the number of rows you have here, the number of variables, is the same as the number of columns you have here, because these variables are the weights for those columns. So this is correct. If you want to actually look at this in terms of the dimensions of the matrix, it all works out nicely. We talked briefly about dimensions of a matrix, which is up by over. So this first, the matrix is, the thing we're calling the main matrix, is a 2 by 3 matrix. The vector x1, x2, x3, you can think of that as a matrix. It would be a 3 by 1 matrix. And notice that these 3's match, and they have to match in order to do this matrix vector multiplication. And furthermore, the 2 and the 1 they combine to make the dimensions of the final guy, which is 2 by 1. And that'll always happen. Okay, next page. So I should just say that, scanning back up here, these 4 ways of writing this, basically, in all cases, this is something you're trying to solve. You're always trying to solve for x1, x2, x3. It doesn't matter whether you write the augmented matrix or the system of equations or the vector equation or the matrix equation. It's all the same problem. It's just different ways of writing it. And they'll all have the same solution, x1, x2, x3. Practically speaking, at the beginning of the semester, this augmented matrix is the way we're actually learning how to solve them, by going to reduced echelon form. So that's the practical way of writing it, but it's helpful to know it can be written all these different ways. So this is a good page to remember. Next page, they're saying what I just said. There are 3 equivalent ways of writing a linear system. Really, we also had number 0, which is the augmented matrix, although by itself, you need to know that there's variables lurking behind and that it represents the system in those variables, but it is a way of sort of writing it down. And I think this is all just saying what I was just saying, that they all have the same solution. So the matrix equation, ax equals b, same solution set as the vector equation. We're writing out the weights with all the vectors, and that's the same solution set as the system with the augmented matrix. It's funny, they included the augmented matrix here, and they didn't include the system of linear equations. There really are 4 ways. Okay. So, now, reviewing vocabulary. If they have a solution, what does that mean? And when we look at this way of writing it from section 1.3, remember what we were doing there is that the A's were vectors, and we wanted to know, can we combine those vectors to get B? So if it has a solution, then we can combine the vectors to get B, and B is a linear combination of the columns of A. That's a phrase that we'll use a lot. Next page. So this is now, I should say on the previous page, they gave you this example, but they never actually bothered to solve it. So you have to just imagine solving that the same way that we do back in 1.1 and 1.2, coming up with a solution, and those are your weights that help you find the vector b, which is 9, -2. Now we're going to try a whole new question where we're going to try to find a linear combination of the columns to find b, except that b is going to be general, and we want to know when can we do this and when can't we do this. So here are our 3 columns. Remember, those are 3 vectors. So there's sort of a picture lurking here in the background. Actually, let me do the axes and a little color coding here. So I'll do the axes in black, and then I'm just going to make up the vectors really fast. Here, I'll make them a lighter blue. Don't worry about graphing. We haven't discussed that yet, but 1, -3, 2, something like that. 4, -11, 8 is something like that. 5, -14, 10, something like that. Okay, so those are some 3 vectors hanging out in R3. And what we want to know is, if I gave you more values for b1, b2, b3, suppose b1, b2, b3 was the vector 1, 1, 5. Can 1, 1, 5 be written as a combination of those 3 columns? You could ask that question, you could solve the system. Could 2, 3, 10 be written as the sum of those columns? Maybe, and you could solve the system to find out. Could -1, -1, -17 be? Maybe, and you solve the system to find out. Now we want to see if we can answer the question simultaneously for all possible values of b1, b2, b3. So, and the way they say this here is the equation ax equals b consistent for all b? Consistent, again, means that there is a solution. Could be 1, could be many, could be infinitely many, but is there a solution? Okay, so we're setting up the augmented matrix here, and when you solve it using reduced echelon form, you just have to keep track of the row operations and how they affect the b's. So we're skipping what all these steps are, but for example, the first thing that happens, I believe, is that you take 3 times row 1 and add it to row 2. So somewhere in there is the operation. Let's see, 3 row 1 plus row 2. That's where you get the 0, 1, 1. But if you apply that to the b's, you get 3b1 plus b2, and that's exactly what ends up going here. Okay, so then, more importantly, when you look at the reduced echelon form, there's a row of zeros on the left. So whether or not this system has a solution is going to come down to this number here, the negative 2b1 plus b3, because a system is consistent as long as it doesn't have a row of zeros and a non-zero number at the end. So I guess the answer here is not. And let me be more precise. So if negative 2b1 plus b3 equals 0, then you have a row of all zeros at the bottom, which you can ignore because that doesn't tell you anything, and the rest of the system has a solution. So then there is a solution. But if negative 2b1 plus b3 does not equal to 0, then there is no solution. So since it depends on what the b's are, whether there's a solution or not, then it's certainly not consistent for all b, only for some of them. And there's plenty of choices that would make negative 2b1 plus b3 not 0. In fact, most choices. So most of the time, there will be no solution. So this is, whoops, up. Sorry, this is most of the time. So now, looking at this same matrix A, we're sticking with the same example, and they're now talking through this. This is just what I was writing before. It's consistent as long as that expression negative 2b1 plus b3 equals 0. So now we're going to study the cases where that happens. Remember I said most of the time it's not 0. But when is it 0? When do we have a solution? Which b's can be written in terms of those column vectors? Okay, well, basically that's our constraint. So if this is true, then B is a combination of A1, A2, A3. So this condition corresponds to a plane in R3. And that's something you learn in multivariable calculus. So we won't really go into the details now. But the way to think of it is that you have all of R3, but then you have this one constraint. So if you have one constraint, then it limits one of your variables. You still have two free variables left. So that gives you a plane, sort of a rough way of thinking about it. Okay, so this picture is the plane, negative 2 b1 plus b3 equals 0. That's the set of points that are a combination, that can be written as a combination. So I think I had to, before I'd written the vectors, when I drew my picture, I drew them from a different perspective. So from this perspective, they'd be something like this and this and this. And they'd all be part of this plane here. So what's going on is that, and I'm not drawing these exactly correctly, but there's three vectors, A1, A2, and A3. And this plane is the plane determined by those three vectors. And so B is a combination of A1, A2, A3 if and only if it's on the plane determined by A1, A2, and A3. So as long as you've got a B that's on the plane, then the system has a solution. So all of these values of B, so these b's have a solution. But if you start taking b's that are over here, and they're not on the plane, these b's have no solution. Oops. Okay. So I don't know if you want, so maybe it helps to have an actual example of some numbers. So let's see, what's a vector where negative 2b1 plus b3 equals 0? So suppose so for example, if I make b1 1, then negative 2b1 plus b3 equals 0, so b3 is to be 2. I could put anything in the middle, like 3 or something. So there, negative 2b1 plus b3 equals 0. So the vector 1, 3, 2, maybe that's this guy over here. That's on the plane. But some guy over here, let's say negative 10, 0, 1, that doesn't have the property that negative 2b1 plus b3 equals 0. Right? Over here, negative 2b1 plus b3 is not equal to 0. And those vectors are not on the plane. That's an example. Okay. And there's a useful word here, span. We talked about that the other day, the span of a set of vectors. So the span of a1, a2, and a3 is that plane. And the b vectors that are on that plane are the ones with the solutions. Or the b vectors, you can also say the b vectors that are in the span. Being in the span and on the plane are the same thing here. Okay, next page. Now we are looking at a situation. I'm going to draw this down here. This is asking the question if any b can be expressed as a linear combination of the columns. In other words, what if you're in a situation where everything in R3 is in the span? So, look at my axes. And the b vectors were red, I think. So if all possible v vectors everywhere, if all b can be written as combinations of a1 through a3, then a1 through a3 span, sorry, let me stretch this up a little bit. Oh, I'll erase those later. Then a1 through a3 span all of R3. In other words, they don't just span a plane, they span everything in 3 space. Okay, so that's just one of the cases where everything is a solution. Now, and that's the thing that we say, that the columns span all of R3. That's, sorry, redundant with this definition here. Okay, now we get to a big theorem. So this is a theorem about this situation, the ones where every possible b can be written as a combination. So that's what I just said is this guy here. So every b can be written as a combination. And we just said that's equivalent to saying that the column vectors span all of R. In this case, R to the m. They're going for a general vector space of dimension m. And if every B is a combination, then every B has a solution when you set up the matrix equation. So these first three, A, B, C, are all just restating, almost by definition, these things that are all connected. D is about the mechanics of the actual matrix, and I actually prefer an additional way of saying it. When did we not get a solution? When did we have a problem? We had a problem when there was a row of all zeros in A. So if there's no problem, if everything has a solution, that means we can't have a zero row in A. So I'm going to add E here, which is, and this is the reduced echelon form of A. So E says the reduced echelon form of A has no zero rows. If that's the case, then we'll never have an inconsistency, we'll never have a problem, we'll always have a solution. So it should be clear why E gives you C, B, and A. D is just another way of saying that, because D is another way of saying E, because if A has a pivot position in every row, then there can't be a row of zeros. If there's a zero row, then there's no pivot in that row. Remember, we're talking about if that's the augmented matrix, A is only the left half. So in A, if there's no zero rows, then there has to be a pivot in every row. Okay. So the next page is just explaining the theorem, and I think I'm going to skip this because, in a sense, this is, well, I'll just fill it in quickly. This is what I've already sort of talked about. So, as I say at the top, A, B, and C are just all the same based on the definitions we've been using. Now we're linking it to this idea that there's a pivot in every row. Okay, so suppose D is true. That means there's a pivot in every row. So when we row reduce the augmented matrix down to U, which is going to be reduced echelon form in D, that means we're saying that every row of U has a pivot. That means there's no pivot in the last column of UD. In other words, that the D can't have the pivot position, i.e. it's not the case that you get down and you have a whole bunch of zeros here, and then a D something. Like would it be M? Sorry, this is an M by N matrix, so this would be like DM. So if every row of U has a pivot position, then you can't have a row of zeros. So as long as you don't have that, then A has to be consistent. Sorry, A is true, because the system is consistent. I would say, so the system is consistent. So A is true. Okay. Now suppose D is false. That means the last row does have all zeros. So i.e. now we have 0, 0, 0, 0, D, M. And then suppose D is a vector with a 1 as the last entry I see. So they're saying, well, in this case, we can even look at a particular example. Then in this particular example, it's inconsistent, and that means there's no solution in this particular case. So A is false, because A said there was always a solution. All right. So the gist of that, again, just to go back here for a second, the point is that we're trying to solve these things for all B, and whether or not it's solvable comes down to whether or not you have a row of zeros, which is the same thing as saying that there's a, so having no zeros is the same as a pivot position in every row. That's the useful feature of the reduced echelon form to look at. Example. Now let's do an example. Good, we need examples. So here's a matrix A and vector B. Is it possible to solve AX equals B for all B? Well, it depends on whether there's a pivot in every row. So, whoops. So, only if there is a pivot in every row. That's the whole point of the theorem. Aha! But A has only 2 columns, and therefore it can have at most 2 pivots. We're not even going to bother reducing this to reduced echelon form. We know by looking at it, it's impossible for it to have a pivot in every row. So, and again, this means that there will be a 0 row in the reduced echelon form of A, which you should be able to see just by looking at 1, 2, 3, 4, 5, 6. If you reduce it, you're going to have to end up with a row of zeros at the bottom. Excuse me. Since A does not have a pivot in every row, then AX equals B is not, I would say not consistent, not solvable for all possible B according to theorem form. Just make sure I'm not missing some. Yeah, I think that's probably what they mean is not solvable. You could also say consistent if you want. Not consistent. Okay, we're almost done with this section. One more example. Good. More examples. Examples are good. So here we're going to actually have to reduce the matrix because there are 3 columns and 3 rows, and that means there could be 3 pivot points. So there could be 1 pivot per row. So we won't know until we actually reduce it if that's the case. Okay, so I'm going to start out, let's see, I'll write my, where am I going to write that? I'll write here, row 2 minus 2 row 1, and that's going to be, so I start with 1, 2, 3, 2 minus 2 times 1 is 0, 4 minus 2 times 2 is 0, 6 minus 2 times 3, is 0. So we've hit a problem already. Sorry, making a bit of mess down there with my palm. So already we know that we can't have a pivot in every row. So that already means the columns of A, how do we finish that? It means we can't always solve it. It doesn't always span, but the columns of A do not span R3. And again, that means that 1, 2, 3, 2, 4, 6, 0, 3, 9, B1, B2, B3 is not always solvable. These last 2 things at the end here refer to the general method for multiplying matrices. So I noticed that these page numbers were wrong because I think they're from a different edition. So just read example 4 and example 5 in section 1.4 in the book. If you want to look at what this generalized matrix multiplication looks like, or you can just wait until 2.1 and then we'll cover it more directly. And at the end, there's just a short theorem about the properties that these guys satisfy. So, quick way to think about, for example, number A, if you look at the right-hand side, if you have A times U plus A times V, so U is a set of weights for the columns of A. AU means add up the columns of A with the weights U. AV means add up the columns of A with the weights in V. And if you add those together, it's the same thing as if you just added the weights for U and V and then multiplied them by the columns of A. You get the same result. That makes sense. And then B says that if you have weights U and you multiply it by the columns of, actually, look at this side first. If you have a vector U of weights and you multiply all those weights by C and then multiply them by the columns of A, it's the same thing as if you multiply the whole matrix A by C first and then multiply by the weights in U. These would be straightforward with numbers. But I think this has been a long enough lecture, so I think I'll stop it here.